This is lecture 19 of M223. In last session, we have seen some result that is called Rolle's theorem, and as a consequence, we have seen what is called a mean value theorem. In this session, we will see some examples, one or two examples, not more than that, of functions that are not differentiable. Differentiable functions you already know. When I mentioned some examples. Now we will see two examples, at least, that are not differentiable. So, as I have said before, given two differentiable functions, their sum is differentiable, their product is differentiable. So, these operations allows you to produce more differentiable functions from a given differentiable function. So that means you have sufficiently many differentiable functions. So now we will do some examples that are not differentiable functions. So let us take some function or let us take a x2 cube root of x. If I am writing here square root of x, I should not be allowing negative numbers, but here it is okay that given okay for minus 1 cube is minus 1. So even for negative numbers, this makes sense for negative numbers as well. So this is a genuine function. Now we are looking at the differentiability of this function at say 0. 0 is an element of R. F is defined on R. We are checking whether f is differentiable at 0 or not. So one reason to write down to focus on differentiability at 0 is the following. We will see now what I am going to do. So what is the definition of differentiability of f at 0 involving limit is the following. Limit h goes to 0, f of it is 0 plus h minus f of 0 by h. So 0 plus h is h. So limit h goes to 0, f of h, f of 0 is 0, so I am not writing that, and by h. So this is limit h goes to 0, cube root of h by h. So we should check whether this limit exists or not. Now, so if you recall, how did we compute limits of some function? Suppose limit x goes to a, f of x. Suppose we have to compute this limit. Then first of all we should be guessing some element a to which this is the value. Then we should take some random sequence that converges to a and show that f of xn converges to this capital A. That is the usual procedure to compute limit. To say that limit does not exist, this limit does not exist, the usual strategy is to look for two sequences xn and say yn that converge to a, and say fxn converges to something else, f1 converges to some other element. I mean there are two sequences converging to same element this a, but their images converge to different elements. That is the strategy to say that this does not exist, limit does not exist. So let us check here. We are trying to see whether this limit exists or not. Now, so we should think of some sequence that goes to what? 0 is the reference point here. We should think about some sequence that goes to 0. I have said multiple times, the only sequence I know that goes to 0 is this 1 by n. 1 by n goes to 0, this sequence goes to 0, or maybe their cousins, say 1 by n square goes to 0, n cube goes to 0, and then something similar. Now we have to, let us check at least for this sequence, can we say anything about the corresponding image. So now we are looking at cube root of 1 by n by 1 by n, where does it go to, that is the question. So now it has a cube root of 1 by n, it is not very comfortable to do this computation. I want to get rid of this 3. So, what we will do is, let us consider the following. Let us change this sequence into n cube, right. 1 by n goes to 0, 1 by n cube goes to 0. So, let us change this. Now, this is cube, now this is cube. What is cube root of 1 by n cube? That is 1 by n by 1 by n cube. What is this? 1 by n square. No, 1 by of 1 by n square, that is n square. Does it converge to any place? Do we know that? N goes to infinity. Where does this sequence go to? Now I understand. Now I assume you understood what is happening here. That if I take this sequence 1 by n cube, that goes to 0, but the corresponding image of this function, this evaluated at 1 by n cube is n square, and this sequence does not converge. Forget about converging to some place, it does not converge at all, it diverges. So, this limit does not exist. So, that says this function x goes to cube root of x is not differentiable at this point 0. See, one reason why we have started with 0 is f of 0 is 0, so we can really get rid of this. 0 plus h is h, so we can just remove this. So, that is an easy place to start. So, that is why we have started with this 0 point. So, we have seen that for this function cube root of x, we have seen that it is not differentiable at 0. So, is it differentiable at any other point? That I am leaving you as an exercise. Check for yourself. Suppose you take the point 2 belongs to R, f is defined on 2, f is defined on R, so it is defined at 2 also. So, one can ask, is this function f differentiable at this point 2? So, we should look at a corresponding sequence that goes to 2 and look at the corresponding limit. F of 2 is not 0, so there will be some other elements that are coming here. We should compute appropriately. So, this is one example of a function that is not differentiable. I mean, it may be differentiable at other points of the domain, but we have a function that is continuous. See, this is continuous. We have a function that is continuous, but there is a point in the domain of the function at which f is not differentiable. This is one example. This is a very standard example, and this is a very standard trick. That previously I was saying 1 by n, then it was slightly uncomfortable for me. So, I want to get rid of this 3. So, how do you get rid of a cube root? You put cube and this cube root will go. So, the 1 by n cube, cube root of 1 by n cube is 1 by n. 1 by n cube I am writing as it is, and this gets cancelled and it gives you 1 by n square, 1 by n square, same thing as n square. But this sequence does not converge. That says, with using that idea, we have concluded that f is not differentiable at 0. Let us try one more example. Again, it is from R to R, x goes to mod x. Previously, we were dealing with a cube root function, now we are taking this mod function. I am assuming you know what is this, that this is a function defined in the following way. For an element a belongs to R, if a is positive, it is assigned to just a, if a is negative, it is assigned to minus a. If a is 0, then it is assigned to just 0. So, this is the way this function is defined. This f, this we are calling as modulus function. This I have already mentioned in the when we are dealing with continuous functions, but anyways I am saying one more time the definition. Now, again we are looking at the differentiability of the function for the same reason as before. One nice place to start is 0. 0 is an element of R and f is defined on R. So, one can talk about differentiability of f at this 0 point. Again we do the same thing. We should compute limit of some function f of 0 plus h minus f of 0 by h. F of 0 is 0, there is nothing to write, 0 plus h is h. So, this is same thing as limit h goes to 0 f of h by h. Now what is this? This f of h is mod h. So, limit h goes to 0 mod h by h. Now we should be computing limit of this. As I said before, one nice thing that can happen is you take without much struggle, you take some nice sequence, and you have seen that the corresponding image is not convergent at all. But this is the less nicer thing. This is the best thing, that you have some sequence for which the corresponding image is not convergent at all. And the next best thing is this, that there are two sequences that converge to the same element, but the corresponding images converge to different elements. So that is the second best thing. I mean, if you are trying to prove that something is not differentiable at some point, that is the second best thing. So for this, again we are looking at a sequence that goes to 0. As I said, the only sequence that I know that goes to 0 is this 1 by n. 1 by n goes to 0. Now we have to evaluate this at 1 by n. So let us do that. 1 by modulus 1 by n by 1 by n, but this is an positive, so this is 1 by 1, that goes to 1. Nice. Okay, maybe let us do one more sequence. Maybe it is so nice here. Previously, if you took that sequence 1 by n cube, it was not convergent at all, but here it is converging. So also maybe this exists, we don't know. Let us try with another example. 1 by n square. So if I take 1 by n square is positive. 1 by n square, modulus of 1 by n square is simply 1 by n square. So I have written here 1 by 1, but I really mean it's 1 by n square by 1 by n square. Previously it was 1 by n by 1 by n, now it is 1 by n square by 1 by n square, and again this gets cancelled, and it is simply the constant sequence 1, so it converges. So for two sequences it is happening same thing, but observe that we are not really making use of this function mod. So even if this mod is there or not there, it doesn't really seem to matter at all. So now when does modulus matter? When there is a negative number associated to that. So only when we take some negative value, then mod gives a difference. So if I take a that is less than 0, it gives minus a. So maybe it is a bad idea to look for sequences that are all positive. Let us take a sequence that goes to 0, but there it is negative. The elements of the sequence are negative numbers. So do you know some example like that? As I said, I know 1 by n that goes to 0, minus 1 by n also goes to 0, right? Now let us look at the image of this function in these elements. So what is this? Minus 1 by n mod by minus 1 by n. As I said, this is negative. So if I take the corresponding modulus, I get a minus of minus 1 by n, that is simply 1 by n. If I take and I still have this one minus 1 by n. So this gets cancelled, but there is a minus 1, so this is constant sequence minus 1, and it converges to minus 1 only. So now there seems to be some effect. If I take a negative sequence, the corresponding thing is converged to minus 1. If I take a positive sequence 1 by n square or 1 by n or 1 by n cube, that is going to 1. So this says for this function at this point there are two sequences xn and yn. Xn converges to 0, yn converges to 0, but if xn converges to 1, if yn converges to minus 1, what does it say? That this thing does not converge. Okay, I am using f here, and I said f before also, that f is different from this f. By f I mean this whole thing. So for this function modulus, there are the one I have mentioned here. For this function, it is not differentiable at 0 because of the reason that I have given just now. For this function, there are two sequences that goes to 0, but the corresponding images goes to different elements. One goes to 1, the other goes to minus 1. So again, just like in case of differentiable functions, suppose I give you two differentiable functions, you can produce differentiable function just by adding them or subtracting them or by multiplying them, or if I give a differentiable function that is nowhere 0, then you can produce new function, the 1 by f, the multiplied inverse of the function, that is differentiable. But such kind of nice thing we cannot expect that from non-differentiable functions, because by definition they are not nice. And observe that even though this mod function is not differentiable at 0. If I do the same thing that I have done for differential functions and take the product f times f, what does it give? It gives mod x square, which is something as x square, but that function is differentiable at 0. Even though f is differentiable at f is not differentiable at 0, f square is differentiable at 0. So this kind of so we cannot expect to produce new differential functions, new non-differentiable functions from old non-differentiable functions so easily. But we can of course produce a non-differentiable functions, but not in a very obvious way. That for this function, it's not differentiable at 0, but the square is differentiable at 0. So we can't expect that we can do it very easily, but we can of course do. I'll give you some examples in the lecture notes of how do you produce a, I mean, what is the first best thing that we can expect from a non-differentiable function. Can we do that something like that here also? Here suppose I take f cube, the cube root x is not differentiable at 0. So suppose I take f cube, f times f, that is so this cube root of x to the power 3, that is simply x, that is identity function, that is differentiable at 0 in particular. So that's what you should think in, keep in mind, that non-differentiable functions are not nice by definition. So it is not very straightforward how to produce a new non-differentiable function from old non-differentiable function. But as I said, I'll give some examples in the lecture notes, extra examples. So these are the two examples. That's all. We will again go back to the theory. So these are two non-examples of non-examples. Now let us recall. So where did we stop in the last session? We have mentioned some result called mean value theorem. What does it say? Suppose I take a function f that is differentiable, and if I take 2 points a and b in U, then there is an element c belongs to a comma b, such that what do we have? F of b minus f of a is equal to f dash of c times b minus c. This is what we have. Let us do one more thing. Suppose I take a different other differential function on the same domain. So say g is from U to R. Again a and b belongs to U, so this U also. So for this a and b belongs to U, there is a c belongs to a comma b, such that g of b minus g of a is equal to g dash of c times b minus a. See, one thing to observe is this c and this c may not be really same. So just for to give this information, let us write here CEF. So this is CEF, and let us write here CG, and now suppose, just for suppose, for these two functions, let us assume just for some time that there is a single c in AB that works for both this and this. That means what? We have FB minus FA is equal to f dash of c times b minus a, and we have GB minus GA is equal to, here now it is g dash of c times b minus a. Suppose we have this situation. Now what can you conclude from here? I am assuming that f dash c and g dash c is non-zero, so one can get rid of that from this place by pushing it here. So f of b minus f of a by f dash of c is equal to b minus a, and because I said g dash of c is non-zero, we are assuming that it is non-zero, then one can get rid of that from here by just pushing here. Then we have b minus c, b minus a is equal to g of b minus g of a by g dash of c. Again there is an inequality, two inequalities, so you can get rid of one of the inequality just by pushing it to the left side. So we have this situation. Again I am assuming g of b is I already said that a not equal to b, So G dash C is non-zero, which means this is non-zero. So I will just push it here and I will just push this here. So what do we have? We have FB minus FA by GB minus GA is equal to F dash of C by J dash of C. So assuming there is a single C that works for both F and G, two differential functions on the same domain, we have said that we have this property. Now without assuming such thing, this is actually true, that suppose you give any two differentiable functions F and G from U to R, this result is true, that there is an element C belongs to A comma B such that FB minus FA by GB minus GA is equal to F dash of C by G dash of C. Now using this F and G, we are constructing a new function capital F from U to R. How is it defined? F of x is equal to Fx minus Fa minus Fb minus Fa by Gb minus Ga times Gx minus Ga. We need to push this, it is Ga. Now what is f of a here? F of a is this is anyways f of fx minus fa is 0, so that is gone, and Ga minus Ga is 0, so that is also gone, and this is 0. What is f of b? F of b is fb minus fa minus gb minus ga, this gets cancelled, fb minus fa minus of fb minus fa is 0. So again whenever we have a differential function and there are two elements a and b in the domain of the function such that fa is equal to fb, then you know there is this element c belongs to ab such that f dash of c is 0. What is f dash of c for this? This is constant, so there is nothing you can do, so the derivative is 0. So in this part gx is there, gx has some coefficient, but this thing is constant, even though there is some coefficient, the derivative is 0. So the derivative of f only matters for this portion and this portion. So what is it? F dash of x is equal to simply f dash x minus this is constant, I am writing as it is, fb minus fa by gb minus ga times g dash of x. Then we said there is a c belongs to ab such that f dash of c is 0. So that means what? If I put c at every place, it means this is 0. So when something is 0, we will not write that, and of course I am just pushing this to this side. So what we have is this, because g dash c is non-zero, I can push it here and get f dash c g dash c is fb minus fa by gb minus ga. This is what we have for two differential functions on the same domain, on the same subset of R. There is a c belongs to IAB such that f dash c by g dash c is fb minus fa gb minus ga. Now why are we doing this? This thing should remind you some relation that you already know between f by g and f dash by g dash. Yes, I am assuming that some of you might have guessed what is going on here. So a result that relates these two things, one of the results that relates these two things is what is known as a L-Hospital rule, right? So what is it? Suppose you have again f and g are from U to R. Suppose you have some element A such that f of x is 0, and similarly g of x is equal to 0. In that case, it looks like that see it looks like for this function the limit is not defined. Limit x goes to a fx by gx. It looks like, I mean, that is the first mistake. It's understandable that it's possible to think like that, but it's a mistake to think that this function doesn't have a limit at as x goes to a, just because for the top we have a limit 0, for this denominator we have a limit 0. But we will see that whenever we know that for these two functions, limit x goes to a f dash x by g dash x, whenever we know for the derivatives, suppose this limit exists, then this limit also exists and these two are same. Suppose we have two functions f and g that are differentiable and all whatever I have said before, such that there is a point a at which limit x goes to a fx is 0, similarly limit x goes to a gx is 0, then in the first look it looks like that for this function limit doesn't exist, but that is not true always. Whenever I know for the corresponding derivatives, if I take that, if it's differentiable, so I can talk about f dash, g is differentiable, I can talk about g dash. So if I take this function f dash x by g dash x, see I am assuming that this is non-zero. I mean, whenever I write something in the denominator, I am assuming it's non-zero. So whenever this limit exists, then it turns out that this limit exists and they are actually same. This is what you know as the so-called L'Hospital rule. So let us prove that now. And how do I even think about proving in that way? I mean, what is the first step? See, observe that there is a relation between f dash c by g dash c. That's what we have on here, and there is some difference here. It's not very straightforward. How do I even start that? But let us start somewhere and then proceed further. Now, okay, at this a, we are trying to look at this limit. Let us assume that this limit, we are assuming that that limit exists already. Now what? See, I have mentioned that this is f is continuous. So see, this I mentioned in this way. I can simply say f of a is 0, that I could have said, but this gives you, this kind of writing gives some misunderstanding that this doesn't exist. So that it is not to misguide you, but it's a way, I am trying to give some caution that even though this is the case, this thing might still exist. That is what I am trying to say. This inverse f of a, this inverse g of a, right? G, f and g are differentiable, so they are continuous in particular, and f a, this is just f of a, this is just g of a. Now assuming that this limit exists, we are trying to see that this limit exists. What is the first step to compute a limit of something as x goes to a? We should look at sequences xn that goes to a. Now what we do is the following. We should be looking at some sequence xn. We should try to produce, or maybe there is some obvious things, obvious guess of sequences that goes to a. We should make use of that and see whether we can go from here to here. That is the whole idea. See, given some point a here, and I say that some sequence goes to a, the elements can be here, 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 here. It can be there alternatively, but that is not useful for us. What we are asking is there is a sequence, say on the positive side or on the negative side. So I am saying there is a sequence that goes to a, and every element is to the left side of a. So xn is less than a for every, maybe after a certain stage, or from starting itself. I can make that kind of choice for every n greater than n. Now, what are we trying to do here? We are trying to use this idea, this result. For that we need two elements of the domain at which f and g both are differentiable. I mean, if f and g are differentiable on the domain, so for 2 points. So we are looking at 2 points. So these are the 2 points. So for a fixed n, we are taking 2 points xn and a, and because I am assuming xn is less than a, the previous result says there is a Cn belongs to xn comma a, such that what do we have? F dash of Cn by g dash of Cn is equal to what is it? F of a minus f of xn by g of a minus g of xn. What did we say about f of a? F of a is 0, so I am not writing that. G of a is 0, so I am not writing that either, and minus minus gets it goes to some place, and we have just this. Now, what I have said before is xn goes to a, Cn is an element between xn and a. If xn goes to a, Cn should go to a. This is not very surprising or too difficult to prove. If you do not know this already, prove that now, that if I take a sequence xn that goes to a, and Cn is an element between xn and a. See, for any arbitrary sequence, it need not be of this form. What I am saying is, for sequences that are of this form and Cn is in between xn and a, if xn goes to a, Cn should also go to a. That is the whole thing. Now, Cn goes to a, and this limit exists, right? So we have a sequence that goes to a. So this should go to so limit x goes to a, f dash of what is it, x by g dash of x. So that says that if I take the corresponding limit, let me do that. So f dash of Cn by g dash of Cn, this goes to something. Now this is same thing as this. So because I am already saying xn goes to 0, so wherever this limit goes to the same place, because they are same, so to the same element, this limit should also go to. So that says limit x goes to a, fxn by gxn. This limit exists, and that is exactly same thing as this limit, whatever it is, and that is same thing as this limit. Where is it? That is same thing as this limit, because I can take into sequences, the limit should come to the same thing. So there is a single element, and that's what we are writing in this way. So that says limit x goes to a, fx by gx exists and equal to limit x goes to a, f dash x by g dash x. This is what it is. Whenever we know that this limit exists, then this limit exists and is equal to this limit. And the starting point was simple. Somebody was told me that f is 0. So now I am afraid to write down something like this, because I am assuming that this limit does not exist. But that is not necessarily true. If I know that this limit exists, then this limit exists even though f a is 0 and g a is 0. And how do I know that? How do I convince myself that there is such possibility? Let us take some example and then see. So let us take the very basic example. I am just asking that limit x goes to a, fx is equal to limit x goes to a, fx is 0. So one nice thing is just take the x minus a. For this, if x goes to a, this goes to 0. F of a is 0, right? So let us take other example. We need two functions, right? Fx and gx. So now I have to take some other function, so that the g of a is 0. One can use just this, right? We will use just that. Fx equal to gx. So see, fa is 0, ga is 0. So this this lives in the previous setup. That's what we want, right? That's what we want. Fa is 0, ga is 0. But see, limit x goes to a. What is fx by gx? Fx and gx are same functions, so this gets cancelled. So it's limit of a constant function that exists always. So this says, so this suggests that even though fa and g are 0, this limit might exist. Let us check the f dash and the g dash. What is f dash? That is 1. What is g dash? That is 1. What is f dash x by g dash x? That is just 1. And we have just now seen that this is also 1. So and for a constant function, limit always exists, and those two are same. Both are 1s. So this is to tell you that even though if you are considering some fraction, something like fx by gx, even though fa and ga both are 0, if you consider the corresponding fraction fx by gx, the limit might still exist. It's not necessarily that it exists always. Limit might exist whenever you know that the corresponding, if I take the corresponding derivatives f dash x by g dash x, if this limit exists, then this limit exists, and that is the L-Hospital rule. So mean value theorem gave some result. What is it? This result. Mean value theorem is for only one function. Then as a consequence, we have said, suppose I take two functions, can I expect a single element C that works for both, and that gave this possibility. And it turns out that even if I don't come in that direction, this is still true. This is also called mean value theorem. This is called Cauchy mean value theorem. I think that is called Lagrange mean value theorem. I am not very sure about the name, which is called Cauchy, which is called Lagrange, but both of them are correct. Both of them are called mean value theorem. And this suggested that I mean, just by the first look, it looks like there is some relation between f by g and f dash by g dash. And the first thing that should come to your mind is we are trying to do something with the L-Hospital rule, and then we have seen just now that what is L-Hospital rule. Yeah, that is a consequence of mean value theorem. Now let us do one more maybe one more application of mean value theorem. I'll write down. I'll recall again what is mean value theorem. Suppose f is a differentiable function, and I have two elements a and b. Such a and b belongs to u. I don't know yet whether f of a is equal to f of b. Otherwise, I will be in the Rolle's theorem setup. What is Rolle's theorem? Suppose I have a differentiable function and I have two elements a and b such that f a is equal to 0, f a is equal to f b. Then there is a c belongs to a b such that f dash c is 0. But here we are not in that setup. We only have two numbers, two elements in the domain. Then we have element c belongs to a comma b such that f of b minus f of a is equal to f dash of c times b minus a. This is the only thing that we have. So I am just rewriting this in the following way: f b is equal to f a plus f dash of c times b minus a. So what does this really says? I mean, how do I think about this? Suppose I take two elements in the domain of a differentiable function, then the value of f at one element is determined by value of f at the other element plus some correction from derivative of f at some point in the in between a and b. See, once you fix a and b, this is fixed, there is nothing to do, and it says there is some element c such that we have this property. So this is for a differentiable function, one time differentiable function. So how did we do that? Again we have taken the help of Rolle's theorem. That's how we have done. Now suppose f is differentiable two times, in the sense f is differentiable one time and the corresponding derivative is also differentiable, which means f double dash exists. f double dash exists. Now for this we are trying to see there are differential functions whose derivative is not even continuous. So they are of course not differentiable. So now we are focusing to the situation where the function f is 2 times differentiable. That means f dash is differentiable. So it is continuous plus something of course. So whatever happened, whatever works for this result, mean value theorem works for 2 times differentiable function also, and because of some niceness about the derivative, maybe we can improve this approximation to a better level. How much we can improve it is not very clear now, we will try to see how much we can do, but this is what you should try to understand, that this condition that f double dash exists, it is definitely a stronger condition than asking that f is differentiable. So maybe this will of course hold for this function also, and there should be something more. That is what we should be trying to guess. Now how do I do that? Again, for f there may not be any element a and b with f of a is equal to f of b, so I cannot do Rolle's theorem. So again we have to construct other function g. Using that we should try to involve f dash also here. Say previously there is no f dash, now we should try to involve f dash and construct a function g, and then hopefully see, maybe after making some small change, that ga is equal to gb is equal to 0, there is some element c so that g dash c is 0, and then maybe we can land in f dash or f double dash, something like that. That is the strategy. Now the question is, what function should I think about? So g from u to r, what should be this function? For in the previous case, what was the function? Gx is equal to fx minus fa minus g of b, not g of b, that is f of b minus f of a by b minus a times x minus a. That was the choice that we have made for the function f, which is going to be one time differentiable. Then we have seen that g of a, what is g of a? F of a minus f of a is 0, this a minus a is 0, so this is 0, g of a is 0. What is g of b? G of b is fb minus fa, this is b minus a, this gets cancelled, fb minus fa minus fb minus fa, this is gone. So g of b is 0, g of a is equal to g of b, there is a c belongs to a comma b, so the g dash c is 0, and g dash c 0 gave this result. Now let us make a small change. We are trying to involve that f dash is differentiable. So let us make the small change. Okay, now the new function is the following: gx is equal to fx minus, as I said, we will make some change here. The change is the following: fa, we will add something, that is the following, f dash of a times x minus a. We know that, so we are trying to add that add this component, minus fb, again this is just by b minus a, this is x minus a. See, we have made change for fa, we will make a change here also, but here we will evaluate, this is a function of a function in x, so we will evaluate this at b. So that is what, minus f of a plus f dash I into b minus a. I will just push this here so that there is some place. That is gx. Now let us check what is g of a. What is g of a? Oh, okay, I forgot to add something. Here we have made the change from fa to this component, fa plus f dash a times x minus a. Here instead of fa we have written the same thing, but we evaluated it x is equal to b, that is what I have written here. Now there is one more change that we need to make. Instead of x minus a we are taking x minus a square, here is b minus a square. Let us check what is g of a. G of a is f of a minus, this is a minus a 0, so this is not there, this is simply f minus a again a minus a is 0 and whatever irrespective of what this is, so this is just 0 and this is 0. Now what is g of b? What is g of b? This is f of b minus f of a plus f dash a times b minus a minus x is equal to b, so b minus a square, this gets cancelled, and what we have is just this f of b minus f of a plus f dash a times b minus a, and as you can see these two are same but with a minus sign, so that those two gets cancelled and we have 0. So g of b is 0, we have seen g of e is already 0. So that says what? There is element c belongs to a b such that g dash c is 0, and what is that? What is g dash c? Let us write that down. G dash x, let us write down that. That is what? This is constant, there is nothing to do, and this is constant, maybe we will simply write 2 times x minus a, and this has a one thing as x part, other thing is constant, so that we will remove. So what we have is the following: g dash x is equal to f dash x minus, this is not there, this is f dash a times derivative of x is 1, so we will just write that, so minus f dash a, then this we will write as it is, then we will write 2 times x minus a, so 2 times x minus a, there is a minus, and I will just copy paste this, I do not write again, yes. So that is g dash x, and then we are saying that there is some element c such that g dash c is 0. Now unlike the previous case, this expression is not so simple, I do not know how to proceed further. So what I know is just that c belongs to a comma b and g dash c is 0, that is all I know. But observe that f dash is differentiable, so one can talk about derivative of g dash also, because see this is constant, this is simply x minus a, so this part is differentiable as many times as you want, and this is constant, so it is differentiable. F dash is differentiable, this is where we are using. Previously this was not showing up, now it is showed up, f dash showed up. Now f dash is differentiable, so one can talk about g double dash. What is g dash of a? That is f dash of a minus f dash a, that is 0, and if I put a here, this is 0, this is simply constant, so that goes. So g dash a is 0, we know g dash of c is also 0, and a is here, c is here, and b is here, that is what it means, right? C belongs to a b means this. Now let us apply the same Cauchy-Minoili theorem, or no, not Cauchy-Minoili, some Minoili theorem, like Minoili theorem, for this g dash. G dash is a differentiable function for which there are 2 points a and c, not b, a and c, such that g dash a is equal to 0, g dash c is equal to 0. 0 is not relevant, but it only means what we need is just that these two are same. Then there is a element d such that g double dash of d is 0. Now I have to do derivative of g dash also. Let us write down g double dash at x is what? F double dash at x. This is constant, nothing to do, and we need to write the derivative of x is 1. So this part is not there anyways. So we will just copy paste this and write minus 2 before. So let us write that f double dash x minus 2 times this. Now what we know is g double dash of d is 0. So we will just put that. Again this is 0, this is 0, so we will just remove that, and maybe simply write this is equal to 2 times f double dash is equal to 2 times fb minus fa, whatever it is. Now let us push this to the left side. See, we are trying to write down fb in terms of something. So what we have is f double dash d by 2 is equal to fb minus fa plus f dash a b minus a, this whole thing by b minus a square. So maybe I can push this here, and what I am left with is fb minus fa plus b minus a times f dash a is equal to f double dash d by 2 b minus a square. Again I will push this whole thing to the right side. What I have is fb is equal to f of a plus f dash a times b minus a plus f double dash d by 2 b minus a square. Now I am considering this as a slight improvement, in the sense fb is determined by fa, f dash a, previously it was only fa and some other element. Now in the second order there is some other element that is determining this value. So this we are seeing as a slight improvement. Now one can go on, one can just proceed further, and when we start with f being a n times differentiable function, now then we will have fa, f dash a, maybe f double dash a, so on till f power n minus 1 a. Then maybe in the nth derivative part there is some other element that is trying to that is helping us to compute f of b. So this is the so called Taylor's theorem, maybe with some extra remainder. More details about this such kind of theorem you will see maybe in the analysis 2 course, but for now this should be, we should be able to understand this. For second term, for 2 times differential functions we have already seen this, we have seen the proof. For the general function I will add in the lecture notes, if you want you can see that. For n times differential function the whole point is the following: f, the value of f at b is completely determined by value of f at a, the derivative of f at a, double derivative of f at a, so on till fn minus 1 a. Then there is some part, some other element that is helping us to compute. That is the whole point of Taylor's theorem. Maybe with reminder, that is the usual phrase you should add when you are using some other element here. But that's all for this session. In this session what we have seen is 2 examples of functions that are not differentiable. What did we see? Then we have seen this L hospital rule. Before that we have seen the so called Cauchy mean value theorem, and then we have seen what is the Taylor's theorem with reminder for a n-term differentiable function. That's all for this session. In the next session we will see some other maybe some examples, something like that, and that's all. Next session will be the last session for differentiation. After that we will start doing a series of real numbers. That's all.